Hello everyone, my name is Shawana Tabassum and I am an assistant professor of electrical engineering at the University of Texas at Tyler. I also direct the biosensors and bioinformatics lab here in the electrical engineering department. So today I'm going to share one of my research projects on an Internet of Things enabled flexible strain sensor for stem growth measurements. So let's first talk about the motivation behind my research. Radial growth of stem is one of the key indicators for crop health. Stem growth is negatively influenced by different kinds of environmental stress conditions, such as drought stress, soil salinity stress, or that could be even herbivore or pest attack. And these events ultimately affect the crop yield. So it's very important to monitor the stem growth dynamics in real time so that we can identify the crop stresses early and the growers can accordingly take immediate intervention in order to reduce the crop losses. However, there is a lack of real-time and in-situ sensors for agriculture. So as we already might know, wearable sensors have gained a lot of interest in the recent time, especially in the field of human healthcare. However, they are highly underexplored in agriculture. And that is where we really want to contribute. Like our goal is to really adapt these wearable sensors which are already there for human healthcare to agriculture, because these wearable sensors have huge potential to monitor the crop and soil health in real time. And that's why our end goal is to really achieve an Internet of Plant Things, where we will have sensors mounted in different organs of the crop, such as in leaves, in stem, or even in the roots. So that is what my research is, and today I'm going to talk about one aspect of this wearable sensor platform for agriculture. So let's first see how our sensor is designed, the strain sensor is designed. So the goal of my laboratory is to really facilitate roll-to-roll production of sensors, and that's why we chose a very simple craft cutter and used screen printing technique in order to fabricate the interdigitated electrodes of the strain sensor. We chose polyimide as the substrate because it provides flexibility. And as a sensing layer, we used graphene oxide, basically the reduced graphene oxide. Here, RGO stands for reduced graphene oxide, which has a very high sensitivity to mechanical deformations. So if now we look at the flow of fabrication, first of all, a transfer tape was attached to a very thin polyimide sheet. And this interdigitated electrode design was entered into the craft cutter. And then this craft cutter made this pattern on the transfer tape. Next, we screen printed graphene on this electrode pattern. Then what we did was we separated the transfer tape from the top of the polyimide sheet. And finally, we have this graphene electrode transferred to the polyimide sheet, which was the thickness of which was of the order of 125 micrometer. And finally, we drop casted a very thin layer of reduced graphene oxide on top of the graphene electrode. The dimensions of our final sensor was 2 centimeter by 1 centimeter, which is pretty small and feasible enough to be wrapped around the stem of a plant. And this figure B, it just shows the flexible nature of our strain sensor. Then we did some real-time bending measurements with Internet of Things. So to do that, we made cylinders of different diameters using a 3D printer. We really wanted to mimic the stem of a plant with these cylinders, and that's why we chose the diameters of the cylinders in a way that so that these diameters represent the diameters of soft plants, for example, a bell pepper plant or tomato plant. So looking at this circuit board, here we can see that we have this MKR1000 board. It gets signal from our strain sensor, basically the resistance measurements, and then a temperature sensor, which monitors the ambient temperature. So here, if we look at the schematic, so what happens is this microcontroller in this MKR1000 board, it processes the readings from the temperature sensor and our strain sensor, and then select the previously stored calibration curve, because our strain sensor is also responsive to the ambient temperature. So when we will have this strain sensor deployed in an agriculture field, there will be temperature variations, right? So we really need to monitor those temperature variations and accordingly calibrate our sensor so that this microprocessor can choose the correct calibration plot depending on the ambient temperature. That's what it does here. And then after selecting the correct calibration curve, the diameter of the cylinder was estimated from the calibration curve. And then this data was transmitted to a smartphone using a Wi-Fi module, which is what we can see here on the screen of the phone. So using this Blynk platform, Blynk IoT platform, we were able to monitor the stem diameter, which was mimicked through these cylinders, the relative resistance variations, which is the response of our strain sensor, and the ambient temperature all in real time. So we don't really have to be in the field. We can just deploy our strain sensor and then we can remotely monitor all these parameters using this IoT platform. Then this slide, it shows the calibration plots of our sensor. So here, the x-axis in figure A, the x-axis shows different amount of bending strains applied to the strain sensor, and y-axis shows the sensor response, which is the relative resistance variation. So when the strain sensor undergoes a bending motion, then the resistance of the reduced graphene oxide changes, and accordingly, we see those response. Here, how we generated this bending strain was by wrapping the strain sensor onto cylinders of different diameters. And as I said, we chose these diameters so that we could mimic the diameter, the stem diameter of soft plants like bell pepper plant, tomato plant, etc. And here we could also observe that when the temperature was increased from 25 degrees centigrade to 45 degrees centigrade, there was an increase in the relative response of our sensor. And that's how, depending on the ambient temperature, our microprocessor in the MKR board was able to choose the correct calibration plot, and then the stem diameter was estimated. Figure B shows a comparison of our MKR board with a benchtop LCR meter, because our goal was to demonstrate whether our system can accurately measure the unknown diameter of the stem. And we could see that the relative deviation between our board and the benchtop LCR meter was less than 5%. So our sensor could pretty accurately estimate the diameter of stem. And with our strain sensor, we could achieve a gauge factor of 827, which is pretty high, as we will see in the following slide. And the smallest angle of curvature that our sensor could detect was 0.018 degree, which is also pretty impressive. So our sensor can detect very minute deviations in the stem diameter. Then we did some repeatability studies in order to see when the sensor returns to its relaxed state, whether the resistance can return back to the baseline or not, which actually did. Like after a bending and unbending cycle, we could observe that when the sensor returned to its relaxed state, its relative resistance actually came back to the baseline value. So our sensor demonstrates pretty good repeatable behavior, which is again a desirable property for field application. So this slide shows the performance comparison of our sensor with respect to some very recent strain sensors, which are flexible and made with thin films. So as we can see that our sensor is superior in terms of the gauge factor. So we were able to get a very high gauge factor of 827, which basically is the sensitivity of our strain sensor for a very small amount of strain applied. So the range of bending strains that we applied was from 0.53 to 1.39%. So for this small amount of applied strain, we were able to achieve a very high gauge factor. And that's why our sensor is responsive to very small amount of strain. Also, we included Wi-Fi connectivity for remote monitoring capability. And then we actually monitor the kinetics of bell pepper plant under water stress. So the plant was under water stress for 2 weeks, and we monitor the stem diameter over those 2 weeks. So because we were wrapping the sensor to a real stem, that's why we later chose a thinner substrate, thinner polyimide substrate, which was like 25 micrometer thick. And then what we did was we monitored the stem diameter using our sensor and also caliper. And we observed very good agreement between the two. So here this plot shows the diameter of the stem over 2 weeks measured with our strain sensor. So as we can see that over the time, because this plant was under water stress, the stem was shrinking, right? And it's actually started from day 2, right? Very early. So we envision that this kind of strain sensor, which can monitor the growth of the stem, can provide an early diagnosis and quantification of the stress. Like it can send an alert to the growers that this plant is experiencing kind of stress. And then if we can also incorporate some machine learning algorithm and incorporate other kinds of sensors to the plants, then we should be able to also classify the stress. So these are very interesting phenomena that we have observed. So these are some concluding remarks. Our future work will be directed to correlating the stem growth with the metabolite dynamics and ion uptake by the routes such as nitrate phosphate ion uptake. And we are actually making such sensors for monitoring the hormones like phytohormones in plants and ions. And one of my students, he is actually presenting a poster on that where he will present how we are making a sensor for monitoring the hormones in plant leaf. So we have actually made a leaf scale sensor. And then we will also reconfigure our sensor for monitoring the growth of root, leaf, and fruits. So that's all for today. Thank you very much for listening to my presentation. Now I'm open to any questions you might have. Thank you.